large is the area, 6 times 1. But remember, this is just use the formula. 6 times 1 times 6 squared. 6 squares. I'm moving the moment inertia from this line about its own centroidal axis to the centroid of the distribution of Welds. So the IY that is given here is 1 times 6 cubed over 12 because 1 is this direction or dimension, and this is the height, 6 cubed over 12. We have 2 of them. That's what I'm putting here, 1 and 2. The only reason why I had this exercise in here is because I want to show that this, whenever it's to the cube, we're going to throw it away. I'm going to go to the next page, that is page number 7. And page number 7, you have it in Blackboard, but also I'm going to show you a smaller size. These are typical cases of Welds. And one of the most common one, this case 5, we're going to use it later. Whenever we had, for instance, K5, this gives you how to compute X bar based on this dimension. I'm going to size. Whenever we have this case 5, we have B and D. So the location of the centroid is going to be computed as B squared over 2B plus D. And we're going to do it later, this computation. And the computation of I sub P, that means I sub X plus I sub Y, is given by using also the B and the D. On the next page, on page 8, we had typical cases. So it helps you to find the location of the centroid. And you can see that they had it here, the location of Y bar, but they don't have the location of X bar because it's obvious symmetry. And here it's obvious symmetry, so they don't give you the location for this case here. They don't give you a location of X bar or Y bar because by symmetry, we don't know exactly where the centroid is. But this allows you to compute the I sub P for a typical case, but if the case is not in this table, you have to compute it. I'm going to show you how to do it both ways. But this is what I'm giving to you. And this is what I want you to put in your code. This is what I want you to use for the exam. And again, you can see case 5 is what we're going to be using later. Now I had a real example. The last day of classes, I gave you several sheets of paper. This problem was in there. And let me go over this problem before we do anything. What we had in here is a column, and you can see the column here. There's a column with a bracket or a plate welded to one of the flanges. And this is 8 inches of weld. And here we had 12 inches of weld, and here we had 8 inches of weld. So this is a typical C shape of the group of weld. And the thickness of this plate is 916. This is a 12 by 170, and the thickness of the flange is 1.56. We need to know the thickness of this plate or bracket, and we need to know the thickness of the flange. And these are the length of the weld, and just length of the weld right now. We need to know these thicknesses because we need to do the shear yielding, shear rupture. As you know, we need to compare that with the capacity of the well per inch. Here on the top, you can see that PU is 60 kip. The distance between the line of action of this force is only a force in the y direction to the well is 10 inches. So altogether from here all the way to the end, we had 18 inches. The geometry, this is A plus T plus 10, 18. But we're gonna find the eccentricity later. They want to know the size of the well. So they need to know what is the size that we had to use. Before I computed PU, the life load was 30, the depth was 10, 836 for this plate that's called a bracket, and 892 for the column, electrode is 70. So to do the computation, what I had done in here, I have put the well, but with a thickness of 1 inch, just to be able to do the computation. I have put the centroid. I have not located the centroid yet, but this force has to be transferred to the centroid. Whenever this force is transferred to the centroid, there is a moment. So I had this in here, the centroid with the force and the moment. And down here, I did a computation of PU that was 60 K. Any questions so I can continue? So the next page is page 11. In page 11, I'm going to compute the location of the centroid. This in here is 8 inches, this in here is 8 inches, and this in here is 12 inches. So I'm looking at these dimensions, the 8 inch, 12 inch, and 8 inch. So obviously, because of symmetry, we know where the x-axis is. Because of symmetry, we know that if this is 12 inches, this horizontal axis is going to be 6 from the top and 6 from the bottom. The one that we don't know is the vertical, the y. So we need to find the x bar. This is what I'm done in here. Look, I'm using as a reference this line. So my reference is going to be this side. So I'm saying the location of the centroid is 2 times 1 by 8. This is 2 times 1 by 8, 1 by 8, plus, since this is a line, 1 for the computation, but this line doesn't have a distance, that's why I put in here 0. And at the bottom, summation of the area, 2 times 1 by 8 plus 2 times 12 by 1. So this comes at 2.286 from the left. I use the formula. This is in case 5. And if you had case 5, I'm going to put look, in case 5, the location of the centroid b squared over 2b plus d. So I had used this formula here. This is case 5. Using case 5, b squared to b plus d, b is 8 and d is 12. So it comes exactly the same value, 2.286 as before. And I put it here that is the same. So in this case, we can use the table if we want, because if we do the computation by hand or computation by using the formula in the table, give us the same value, because this case is in the table. Now I'm going to compute the value. I have put already the location as a line. I have put the location of the centroid. The centroid we just determined was 2.286 from the left And since we had this is 8, the location from here to the left is 2.286. From here to the right is the different 8 minus 2.286, 5.714. The location of the centroid to the top is 6 and to the bottom is 6 as indicated. So I'm going to do the computation of IX. IX is going to be the moment inertia about its own central axis of this one. There are two of them. So I'm going to use A times 1 cube over 12, and after that, area distance squared. So this is done in the next page. On the next page, you can see I sub x. I had two of them. This is one, and this is the other one. The base is 8. To use the formula, put in 1 cube over 12. And this is small, I throw this away. What is large is the base, the area, 8 times 1 times the distance from this line to the centroid, that is 6. So this is the area times the distance squared, times 2. So this is the moment inertia of this line about its own central axis plus the area distance squared. I'm moving the moment inertia to this line. There are two of them. This line is 12 inches. 12 inches. So if you look here at the bottom of the screen, I sub y, it's going to be the moment inertia about the own central axis. So it's going to be 1 times A. This is a large, a large moment. So if you look at this also, we're going to get in here, I'm going to find the moment inertia of this about the own y-axis, and after I'm going to do the area distance squared. So I'm going to find the moment inertia about this axis, and after I'm going to move it to here. So when you look at this, 1 times a cube over 12, 1 times a cube over 12, give it this moment inertia, plus the area, 1 times a times the distance squared. And from here to here is 4. This distance is 4, and subtracting 2.286 to move it to the centroid. So from here to here is 4, and the centroid is 2.286. So I'm saying 4 minus 2.286 squared. So again, I'm finding for this side and this side, that's 8 inches. I'm finding the moment inertia about the own y-axis. So it's going to be the base 1 times a cube over 12. This is what I have in here. And I need to move it to this line. And the difference between this line and this centroid is going to be 4 minus 2.286. 4 minus 2.286 squared. I'm multiplying the area 1 times a. There are two of them. Now I need to find the moment inertia of this line about its own y-axis. And this is what I've done in here. What I've done in here is the moment inertia is 12. The moment inertia of this line about its own y central axis is 12 times 1 cube, 12 times 1 cube over 12. And this is 1 cube, I'm throwing this away. What is large is 1 times 12, the area, times the distance squared. And the distance squared in here is 2.286. That's what I have in this side. So it is this moment inertia about all central axis that is 12 times 1 cube over 12. Very small, I throw it away. Plus the area, this 1 times 12. I'm going to move it from this line to this line. So I had to use 2.286 square. So after that, I had combined the two moment inertia, ISO X, the 720, ISO X 720 with ISO Y, the 195.05. I want to point out inches to the third because we are not using area, we're using line. So it doesn't have the thickness. We're using the thickness just to do our computation, but it's inches to the third and inches to the third. Whenever we use area, it's inches to the fourth. But for this computation, well, inches to the third. This is the formula. This formula comes from case 4. Case 4 in the table. So this is case 4 in the table. In this table, oh, sorry, case 5. Case 5 in the table. This is the formula for ISO P. This is the formula that I had used in here. From case 5 from the table, ISO P, I had computed by using this formula, give me exactly the same value. So you can see that by using the formula, some cases are not in the table. So we have to learn how to use both of them by computation and by table. It happened that this case is in the table, so it gives you exactly the same value. If the case that you are given is in the table, just use the table with confidence. If the case is not in the table, we have to do the computation like I did above. So we already had ISO P. I'm going to go and do the computation. Look, this is the same problem. How I had computed the moment, if you look at the distance, the eccentricity of this force, just for the people coming late, or they're not there yet, the eccentricity to this point is 10 inches. This 60 to the well is 10 inches. So what I have done in here, I have computed the moment, the force, the 10 inches that is shown to you, plus 5.714. So the moment is 942.84 kips inch in this direction. So I had transferred the 60 to the centroid. I had transferred the moment to the centroid. So this MU is the 10 inches that we had that was given plus this 5.714 location of the centroid from this point. And so give me 942.84. The direct shear means that this force is going to be producing shear forces in this direction, this direction, this direction, everywhere. And that's the direct shear. So resisting the direct shear, we had 8, 12, and 8 more in here. So 8, 12, and 8. That's what I had in here. The direct shear in Y is the force divided by how many inches of well we have. I'm writing 8 here, 12 from there, but in general, you just need to add everything together. I just want to point out that there are 8, 12, and 8 where every inch is coming from. So the force divided by all the lengths of the well gives 2.14 kg per inch in the same direction as this. For the moment, this moment is 942.84. To find the component in X, we use the Y distance, and this Y distance is 6. 942.84 times the Y distance over. This is ISO P that we just computed. ISO P we computed two different ways. ISO P the polar moment inertia. We compute it by using the formula. We compute it also by hand. And this give me 6.18 keep inch to the right. This component here is going to be exactly the same, 942.84, but this is the X distance. And you can see the X distance in here, look, the X distance 5.714 divided by 915.05, that is I sub P. So in this formula, as you are aware from other computations, this distance here remains the same. The only thing that changes is the Y and the X. This gives me 589 kip per inch down because this is the direction of this form. So the resultant force per inch at 0.1 is 6.18, 6.18 the component in X squared, exactly the same way that we did for Welds, for both. 6.18 squared, the component in X, plus all the components in Y, 2.14, and 5.89 squared. The resultant is 10.13 kip per inch. They have to be smaller than either the capacity of the weld per inch or the shear yielding per inch or the shear rupture. So here below, I'm doing the shear yielding. And we already done shear yielding before, but just in case, I have put in here the equation. And remember the shear yielding is in chapter J, very close to where you find the block shear equation. So the phi factor is 1.6, and it's obvious that the gas play control, because you look at the original problem, and you look at this problem, this is 916 with a weaker material 836. And this is 1.56 with a stronger material. So it's obvious that the plate is controlling what they call it the bracket. So I'm doing the shear yielding of the bracket, 0.6 Fy times 916, give me 12.15 kip per inch. In the next page, I have computed the shear rupture. And again, you know what it is, but I'm calling it J4-4. You know where to find it. It uses a phi factor 0.75, 0.6 FU from 836. Again, it's for the plate 14.60. We don't know the weld. We're looking for the weld. And remember, the smallest number control, but we don't know yet the size of the weld. But the size of the weld is the phi times 0.6. The electrode is 70, given on the top of the page, 0.778. Unknown, 22.278. So the force at 0.1 was 10.13. So I'm going to make 10.13 kip per inch equal to the capacity of the well with a known size A. So they give me 0.45, half an inch. I had to compute the capacity, put this back into the equation, compare 1114 with 1468 and with a 1215. So shear yielding, shear rupture, and the weld. And the weld comes as 1114. So obviously the weld is controlling our design, and the answer for this problem is half an inch size of the weld. Any question before I go to the table? Okay, look, for cases with a bracket, we don't use the web thing, right? Uh, Obviously, if you look at, and please feel free to ask questions. Look, the connection is through the flanges. So we do have to use the thickness of the flange. But in this case, it's obvious that it's not controlled. Nathan has a question. What question do you have, Nathan? What is your question? Oh, you have no more question? Okay, so that one. Where did it pen come from? Okay, good. Feel free. Look, do you see the distance from the line of action of the force to the well? 10 inches. This is on page 10. So to find moment, I'm going to apply the force times the distance to the centroid. The centroid is in here. So this distance to the centroid, we need to add the 10. Okay. Any other question, please? Okay. So I'm going to show you how to use the table. So the same problem. To use the table, I'm going to give you time to go to chapter 8, page 92. This is exactly the same problem. And sometimes we can find the same problem, we can find tables that we can use for our problems. And sometimes there's not a table. Some of the homework problems, I ask you to do it both, using the elastic and using the table. So all that we need to know is the eccentricity, EX. And this EX, if you look, when I computed the moment, the eccentricity, 10 plus 5.714, 15.714. This is my eccentricity. So we have to find the eccentricity. This value is 15.714. No. There's a question about the thickness of the well. We are the way we treat the wells as a line. They do not have thickness. And using the one to be able to use the formula, we are used to the base times the height cube over 12 plus the area distance squared. But we don't have that dimension. The dimension is only used for our computation. But the size of the well appears in the formula. When I computed in here, I'm answering somebody's question. When I computed in here, look, 0.75 times 0.670, here will become the size of the well. But the result of the polar moment of inertia is in inches to the third because it doesn't have the thickness. The only reason why I'm using the one is to do the computation. That's why I throw it away, because if you do the computation, it's not a very small number like it is whenever I use the 0.707. Okay. I was answering the question. Only the one is used for the computation. So this is the case that we have right now. The eccentricity, the only thing that we need. The only thing that we need to do our computation is eccentricity and this 8 dimension. Because when you go to page 892, and I know that I don't know why you cannot read the code clearly, but you have your own code. You can see in here the eccentricity. This eccentricity and this value in here. The only thing that we need to know is the value of K and the value of A. And whatever value we obtain from this table in here, you look at this formula, this is the value of C. So this C value in here comes from this table. So when you look at this C minimum, it's going to come from the table. This is the PU. This is the PU. That's also phi P sub n. So P sub U is going to be equal to C minimum times the phi C1 DL. I'm going to explain this formula later. But this is what we had to use on this. Before I forget, there is a question. What would it change if the longitudinal walls are of a different length? Well, the only thing that changed is that there's no symmetry anymore with the weld distribution, that we cannot use the table. We had to do the computation by hand. So the computation of the centroid is going to be more difficult because this, I'm answering this question from Pinara. Since the lengths of the weld are not the same, we don't have symmetry, we have to compute probably the X bar and Y bar. But once you know the location of X bar and Y bar, all that you have to do, moment inertia about the own central axis plus area distance squared. The next problem that I'm going to do is one that is not in the table and is one that you have to compute the centroid and do everything just by hand. So going back to this problem. Eccentricity is 15.714 and the distance is 8. On the next page, look how simple, how easy it is. In the eccentricity X is equal to this letter A is not the size of well, it's a constant to be used for this table. So don't forget that this in here is a constant that we're gonna use for this. And so L in here is the 12 inches. You can see in the code that this is L. In our case, it's 12 inches. So the only thing that we have to find is the value of A. This constant came as 1.31. The value of 8 in the table, KL is given in here. You have your own code. I know you couldn't see that. Equal to 8, so KL is 12.67. We have to go to the table with 1.31 and 0.67. A 1.31. So look, in here I had A 1.2 and 1.4 and interpolated 131. You see K 0.6 and K 0.7. So what you do, you go to this table. Since our value A is 1.3, you can see that 1.3 is not on here. We had 1.2 and 1.4. We have 1.2 and 1.4 for A. So we do not have the value of 1.3. And the value of K is 0.67. K, we have 0.6 and 0.7. So if you look at K equal to 1.2 and you move to the right and you go to 2.6, you find 0.63. You go to 0.7, 1.85. So all that I had done in here, you can see in here, I had gone to the table. For A 1.2, I found K 1.4, 0.6, 163, 0.7, 185. For A 1.4, I found K for 0.6 is 1.42, K 0.7, 1.61, and then the interpolation for 1.31. So I done the interpolation in here, and I have found that the value, this is what they call C mean, found as by interpolation, because we cannot do it directly. Sometimes we do, sometimes we can by interpolation. I found 1.524. PU, I said is equal to phi PCN. This is the formula on the top left of the code. C mean phi C1 DL. So this is the 60 that we used before. This is what we just computed. The phi is 0.75. C1 for electrode 70 is 1. And D is the size of the well in inches. So you can see from here. The C1 for 70 is equal to 1. And the number of 16th inch for the size of the well. So when I saw for this, C minimum 0.75, 1, because we had an electrode that is 70. D is going to be the size of the well in 16th of an inch, and 12 is the length that we use for all our computation. So it came as a 437. You have to go up. You cannot go to 4. You got to go to up to 516. If this were 7, it would be 716. Whatever number you obtain in here, they're in 16. If you compare the answer by using the table with the answer by using elastic method, because it's conservative, the elastic is telling you they have to use half an inch as well. The table tells you that only you need a 516. On the next page, on page 16, I had done again, I call it another way of doing the interpolation. It still gives me the same 516. Any question about this? Yeah, the question is about for the LRFD, the value that we use for fee is 0.75. Whenever we have the LRFD, the fee value is 0.7. And it's he already solved. Don't worry. I know. But asking question is good. Don't worry. Okay. Any other question? I'm going to go to the next problem. I'm giving this problem to you in class also. And if you look at the well, oh, there's another question. How do I get 516? If you read in the code, the D, this D is the size of the well in 16. So the only unknown in this equation, the only unknown in the equation is D. It can 4.37. This is 4.37, 16. We have to go to 516. So everything that you find for the value of D is in 16. If I find 5.5, 16. So everything is going to be in 16. This is given in here. In 16. Yeah, that was a late question that I didn't see. Yeah, you have to round it up because it had to be a standard size of the well, but it had to go up because otherwise it will fail. That answers your question? Look, this is the problem I'm giving to you in class. The geometry, look at the geometry from this point we have 12 inches. So whenever I compute the moment, I'm going to use the 12 plus whatever distance I have here to see. I'm going to have two components, one in X and Y, and one in X. So I'm going to have the 4 times distance. I'm going to be distance eccentricity in X, eccentricity in Y. This is the well, 6 inches of well. 6 inches of well. And also 6 inches of well in here. The distance between this corner and the well is 4 inches. And so from this point to the end, to this corner is 10 inches. This one has 6 inches of well, 3 inches to the top, and 3 inches to the bottom. The thickness of whatever we had in here is half an inch. The thickness of the bracket is also half an inch. And the electrode is a 70, the dead load 10, the live load also 10, the size of the well. And the one in this question is again determine the size of the well. This is a view of the car. So I want you to go to the table, go to this table, and tell me if you can find a case in there that I can use to compute location of a centroid and iso x plus iso y that is the polar moment inertia. And you can see that they're not 1 and 3. No, we cannot use 1 and 3 because of these dimensions in here. So what we have to do, we need to do the computation by hand for everything. It's obvious that the location of the centroidal x-axis because of symmetry. This is the location of the centroidal x-axis. Look, because of symmetry, we know. The location of the y-axis is unknown. So I'm going to use this line as my reference to compute the location of the centroid of the distribution of Welds. After that, I'm going to move the force in Y to the centroid. I'm going to move the force in X to centroid. I'm going to move the moment. So in this case, we will have direct shear in the Y, direct shear on the X, and of course, we're going to have forces produced by the moment in the X and forces in the Y. So on the next page, page 18. No, you don't combine the cases. There's a question about combining the cases because when you combine the cases, these dimensions are completely different. And remember, whenever you find the moment inertia, the area, distance, square is going to change everything. So you have to be very careful trying to combine cases. So again, I'm representing here the component of the force of this force in Y, the component in X. I had drawn again the geometry 4 inches, 6 inches, 3, 6. And number one, we had to determine the location of the central. And number two, we need to move the forces to the central. And like I mentioned before, we consider they are lines, but to do our computation, we consider having a width of 1. So to find X bar, we find in the location of this centroid, we have 2 times the area. Look, this area is 6 times 1 times X bar. So if you look at what I have in here, the centroid, the X from here to here is 3. So this, if you look at what I'm doing here, this is 3 and this is 4. That's where the 7 comes from. The 7 comes from 3 plus 4. You can see that we assuming for a computation that this is 1. But I'm not adding the 0.5 because in reality, this is a line. That's why everything goes to this point. And so we had 6 and 4. The centroid in here is 3. This is 4. This is the 7. This one in here, because it's a line, doesn't have any dimension. That's why I put a 0. Here at the bottom is summation of the areas. 2 times 6 plus 1 plus another 1 by 6, 4.67 from the left. So this is the location of my y-axis. Yes, I'm using the left side as a reference. You can see here the answer. So we found the location X bar. Remember that this is 0 because it doesn't have a dimension. It's just a line. And so 4.67 from the left. And I put in here a note that the formula cannot be used. So I'm going to compute I sub X. And I'm going to compute also I sub Y. I'm going to find I sub P in here. I'm going to increase the size later, but I just want you to do look. I'm finding the moment inertia about the x-axis. All of this group of Welds, all of this group of Welds, I'm going to find a moment inertia about the horizontal or the x centroidal axis. So I had in here This area, they are the same. I put in 2. This in here is the area 1 times 6 times the distance square. The distance square, you can see this 6 square. So this doesn't have this dimension. That's why the distance is 6. So 2 times this area, because one at the top and one at the bottom, times the area, that is 1 times 6, times the distance squared, that is 6 squared. Plus, the moment inertia of the on-axis is 6 times 1 cube over 12. I throw this away. Every time that 1 is to the cube, I'm going to throw it away. Plus, this one, about this axis, that is the same as this, is going to be 1 times 6 cube over 12. So moment inertia of the x-axis is 450. The moment inertia about the y-axis. I need to find the moment inertia about this axis. So I have to find the moment inertia about the own y-axis for this one. There are 2 of them. So the moment inertia about the own y-axis is the base times the height cube over 12. Given here, 2 times, because there are 2 of them, 1 times 6 cube over 12. 1 times 6 cube over 12 give me more inertia about this line. Plus the area distance square. So how I have found the area, look, from here to here is 3. Look, this is 6, so the centroid to the left is 3, and to the right is 3. So 3 plus 4 is 7. So I have in here 7 minus 4.67 squared. To find IY, I had 2 of this, the base 1 times the height 6 cube over 12 is this one. Plus the area 1 times 6, I need to move it this to the centroid. From here, I have to be moved to this line. It has to be moved. So the total, if I have the total distance that is 7 and I subtract 4.67, give me the distance to the centroid square. This one in here, moment inertia of the y central axis is 6 times 1 cube over 12. I throw it away. Plus the area, 6 times 1. But since it's aligned, the distance to this line is 4.67 square. So this is the area times the distance square, 6 times 4.67 square. So this gives me 450 for x, 232 for y. So the polar moment inertia in here is 682. Any question? So on the next page, this is page 19. You can have in here, I just put the well, the 4 inches, the 3, the well, the 3 inches, location of the centroid. And the service load was given. So this is 1.2 times 10 plus 1.6 because both there were 10, 28 K. I have found since the angle is known, I found the vertical component and the horizontal component. vertical component 24, 25 kip, horizontal 14. And the moment about the centroidal axis, about this point, this is producing a clockwise. This is also producing a clockwise moment. That's why I had 24.25. This 20 is the total distance, look, 12. Should be 20. There's a mistake in here, look. What should this value be? 22. Yeah, it's 6 plus 4. And let me check that that's 4. Yeah. Yeah, this should be 22. But look, 12 plus 10, 22. But the difference, 22 minus 4.67, is this correct? Yeah, this is correct because I caught my mistake when I was writing this. I caught my mistake, but I didn't change the number. So this is correct. Um, anybody had a question? So look, just change this number. It should have been 22, but everything is correct. So I had the 24.25 times 17.33. I had the 14. The distance to the centroid is 6 inches. So we have 504.25 inch going in the clockwise direction. So here I'm computing the direct shear first. I had transferred the 24.25 to the centroid. I had transferred the 14 to the centroid. The component in X, the direct shear in X, is the 14, and we have 6 inches of weld, 6 inches of weld, 6 inches of weld, 18. So give me a 4.78 kip, and this should be per inch to the right. And the component, the direct shear in Y is 24.25 divided by the number of inches of weld, 1.35, that should be kip per inch, also going right. Direct shear is always easy. Don't forget the direction. This is the one due to the moment. I did it twice because in here it was too small. I couldn't really understand myself. So I done it in here. We had the moment that we computed 504.25. And here on the top, at the farthest away, I had a component in X that goes to the right, the same as this one. And a component in Y that goes down like this one. Here at the bottom, I had a component, I have put it in here, component in X that goes to the left, opposite to this one. So we had to subtract it. So it's not a good location. And component down is good, the same as the other one. So this is the critical location. Going to the next page. This is page 20. And in page 20, this is the moment that we just computed. The X component uses the Y dimension, and this is I to X plus I to Y. You can see that the Y dimension in here is 6 inches. And the I to P plus I to Y, we computed before as 682. So the component in X is the moment we just computed the Y or I sub P, the I sub X plus I sub Y, 4.44 keep an inch to the right. The component due to the moment Y is the same moment, and 5.33 is the X dimension to that point. And this dimension I have computed from you in the previous page. So the component in Y, I was saying it is the moment, the same moment. This is the X distance and the I sub X plus I sub Y. So the resultant in one is all the components in X, you can see have 4.44 in here. And we have 0.78 in here. So 444 and 0.78. The components, I mentioned all the components in Y, 3.94. And in the previous page, we had 135. So this gives me a resultant of 7.43 kip per inch. All of this give me 7.43. They have to be more or equal to 0.75 times 0.6, that electrode 0.778. From here, A came up 0.333, so 616, 38. I need to check to make sure in here that I'm not going to exceed the maximum. Sometimes, and this is, I'm going to tell you that sometimes it's a trick in the exam. And I don't know if the whole exam that I'm giving to you, it was a problem like this, that people found the size of the well, but they forgot to check with the maximum. So whatever answer you found in here, computational, was right, but you cannot put it in there. You could not perform the well because people forgot to check the maximum. Don't forget maximum and minimum. And any questions? Oh, this is a very good question. Why did we not compute R1 to shear yield and shear reaction? Because I already did it in the previous problem, but you should. I didn't want to go through the computation, but you should do it. Yeah, always, whenever you do the well, you need to do the capacity of the well per inch compared with shear yielding and with the shear reaction. Any other question? No. I'm going to go to the next problem. This is page 21. And this is one of your homework problems too. I just want to point something out about this problem. Sometimes it's very difficult to see how the problem look like. It's obvious that this is a column, a Y flange, and in here we have two angles at 5 by 5 by half an inch given. And this is the service load factor to 15, and they want to know if it is adequate. Everything is given. Look, 5 inches, 5 inches, 5 inches, 316, the size of the well. And electrodes E70, dead load, live load, all of that. And you only want to use the table, only the table in here. So I had put a front view of this to show that both of the angles are on the same flange. So both of them, they're in the same flange. So I'm gonna use 50%, 50% of the load. So there's no need to use the total load. So whenever I find my answer, whenever I find my answer to see if it's adequate or not, I'm gonna look at 7.5 instead of this is the factor load 15. So instead of looking at the total load, because I'm gonna use 50%, 7.5, I have to look at 7.5 only. Because if I forget that there are two angles, and I'm gonna say that it's no good. So this is everything is given. You have to find in here it is adequate or not. So do I need to compute the centroid? I'm going to use the tables on. Do I need to compute the centroid? Anybody? Yes, because the table requires the eccentricity EX. So to go to the table, I need to use the eccentricity EX. So next page, page 22. So this dimension, the 12 is given, the 5 is given, 5 is given. And I had to find, we know where the centroid, the X, I need to find the Y. And in this case, I'm using the right side as my reference. So I'm saying, look, I'm using this as a reference. 2 times 5 times 1, this area, 1 times 5, and the distance from this centroid to here, 2.5. This one, because it's a line, doesn't have any distance, over the summation of all the areas. 2 times 5 by 1 plus 1 times 5. 1.67 from the right. And this is what I'm showing here. This is the location of my axis. So the eccentricity is going to be look, 12 plus 5, 17. So distance all the way to here is 17. Minus 1.67, 15.33. So go to the code to page A-92, the same page that we used before. So are you ready on page H? Okay. Look, this is the page. H.9. Doesn't matter if force is on this side or the other side. But if you look at the values that we need to go into this table, eccentricity 1533 equal to A times L. This constant, not the size of the well, like I mentioned before, 15.33 divided by 5, almost 3. And KL equal to 5.551. So go to the table with the value of A3 and K equal to 1. Well, I don't understand the question that the shape of the member not affect the location of the x-axis. It's only the location of the x-axis is based on the group of well. Like in here. Look, well on the top, 5 inches, 5 inches. So y the white bar, what is you asking me the question? Where is the white bar in here? How many inches? From the bottom and from the top. Look, the white this is the x-axis, so this is the y. So what is this distance and what is this distance? 2.5. Yeah, we only have to consider the well. Remember, we're doing eccentric well. All that we working with right now is eccentric well. We are not looking at this member. We're not doing anything for this member. Remember, right now we're looking at the group of well. So that's a good question. Okay, look, go to the table and with the value of about 3 and K, letter A 3 and K equal to 1. See what you find in there. Okay, this is an interesting question. Look, the question is why we cannot use the X bar from the single angle. And the answer again is we are not doing anything with the angle. We're looking at this group of well. No matter what shape I have in there, no matter if it's an angle or it is a channel, no matter what shape I have in there. But the group of well that I have in there is gonna look like this. So doesn't matter what kind of shape this is attached to. The only thing that we're concerned right now, we're concerned with the well. The same that we did for whenever we had a member, we had to do for tension, we had to do tension yielding, tension rupture, we had to do the blocks here. So here, the only thing that we do it is the well and the force. So this is a group of well, this is a force. So we check in eccentric well. That's why we don't even look at the hand. So whenever you go to the table with a value of about 3 and 1, you find that C minimum is about 1.12. From the formula on the top left of the table, phi C1 DLC sub M, 0.75, the value of, because E70, this is 1. Look at the size of the well that we're using in this problem. 316. So seeing the value of this in 16, we're gonna use the 3. Since this formula requires that this is in 16, instead of 316, we use 3. If we have 416, we use 4. 516, we use 5. And this is the length of the well, and this is the minimum, so it gives me 12.6. 12.6 kip is larger than I was saying using 50%. Okay. Because if you forget that there are two angles, you would say it doesn't work because 12.6 is more than 15, but it's only 50%. So this is added. Any question? So I'm gonna go to do columns right now. Yeah, for for the table, and this is question related to the previous one. For the tables, every size of the well had to go in 16. Like if we had a 516, we only put a 5. And like you say in the 316, we use a 3. The same is the answer. If I'm looking for the size of the well and the answer give me 2.5, that's going to be 316. So everything is in 16. And remember, the letter A for the table is just a constant. Any other question? It should give you the same value. Recompute that table. Yeah, case 5. Yeah, it should give you the same value. It should give you exactly the same value. Yeah, do case 5. Any other question? Okay. Look, we're gonna start a new chapter, and the design of column is so simple, too simple. Sometimes we become overconfident. And first, I want to tell you that chapter E. I want you to go to chapter E first. If you look at chapter E,